Okay, so we're off. Question 1, what are the requirements for current to flow in a circuit? Daniel, you might be able to...
There's got to be a closed switch.
A closed... Well, we call it a closed switch. We might call it a closed path, wouldn't we?
Yeah, right.
A closed path for electricity, which really is the flow of electrons, isn't it? For electricity to flow.
Needs to be a power source as well.
Yeah, also, yeah, we could have a power source.
We can't.
Power source such as a battery, etc. Okay, good. What about the devices? This device here would be, Wooly, what would that be? That is an ammeter. So we need to start recognising these. That's an ammeter. What about Matthew Jones, is it? What about the circle here? A battery. We also know that as a cell. So this is a battery, which is, of course, supplying a potential difference or voltage. Okay. Aiden, what is this? What would we...
That's a bulb.
It's a bulb. Okay, good. Would a bulb have a resistance?
Somewhat, yeah.
I would say absolutely it would. Which would have also a resistance. Good. And this one, what would you call that?
Switch.
A switch. Excellent. And of course, when that switch is closed, we have a path for electricity to flow. Electricity follows the path of least resistance. So what happens if I might just ask this, if I had a connection from here to here, which way would the electricity flow? Would it flow through that resistor? No, it wouldn't. Because this is a resistor and electricity flows through the path of least resistance. Well, in other words, it's more likely to. If I had zero resistance wire connected there, it is certainly going to flow around the resistor. Okay? Now, why do scientists refer to conventional current as flowing from positive to negative? Matt, what did you have for that one? C. Yeah, originally scientists thought charge carriers were positive. So the thing is that although we know that electrons flow from the negative to the positive, we have two things. We have conventional current. We have conventional current, which is what? Good. Conventional current is positive to negative. Positive to negative. Okay, and then we have electron or current flow or movement of electrons is from the negative to the positive. Okay, it's just the way. If we were asked, we might ask you a question: which direction does the conventional current flow? You'll need to recall that. Okay, now let's have a look. What current flows in a light bulb through which a 30 coulomb charge flows in? Well, first of all, Q is equal to 30 coulombs. Now, 30 coulombs is a big charge. Okay, a big charge. Now, of course, time for part A is 10 seconds. Now, we know that I is equal to Q over T. But be careful, T is in what? Seconds. Thank you. So, because 1 amp is 1 coulomb per second of charge. Okay? So, therefore, we can say that the current for part A is 30 divided by 10, which is 3 amps. 1 minute is 30 divided by 60, which is 0.5 amps. And 1 hour, well, we have to do divided by, it's 30 divided by, how many seconds? 3600. Okay, all right, well, we can cancel that 0 out. How many times does 3 go into 360? 120. So I could cancel that out, and we can say that that's 1 over 120 amps, which, of course, we could work out in our calculator as what? What was the answer?
Is it 1 over 120 or 1 over 12? 120.
1 over 120. Oh, now look, you could put that in your calculator though, but I've just simplified that as a fraction. What is that as a decimal? What is 1 over 120? Well, let's get our calculator out and we go 1 over 120 is equal to, now of course I get that, 0.00833 for example. Now, what happens if I was to say I would like to one decimal place, I'd like that in milliamps, please. What do I have to do? What do I have to do for milliamps? I know that milliamps is 10 to the power of negative 3. So I'm going 1, 2, 3. There we go. 8.3 milliamps. Okay? Or we could say 8.3 by 10 to the minus 3 amps. So you do have to know your millimicros and stuff because we'll be sort of referring to those later. Okay, now a car headlight. I'm going to rub that out just for the second. Give myself some room. Car headlight may draw a current of 5 amps. How much charge will have flown it in? Well, look, it's more of the same thing, isn't it? Okay, but this time we've got Q is equal to I times T. So for 1 second, we've got 5 times 1, which is 5 coulombs. Is that right? 1 minute. 5 times 60. 300 coulombs. And 1 hour. 3,600 times 5. Is that 18,000? 18,000 coulombs? I haven't used a calculator. I hope I'm right. Okay, 18,000 coulombs. So pretty much at this stage, still looking at that. All right. Now, let's have a look at question 6. In a solution of salt water, a positive charge, we could say of 15, so I could have a potential here, 15 coulombs. 15 coulombs of charge, positive, seen to move past the right in 5 seconds, and the same total of, and in the same time, a total negative charge of minus 30. So what's the net charge?
Negative 15.
So the net charge is minus 15 coulombs. Okay, so what was the current through the solution during this time? So, of course, I equals Q over T, which is negative 15 coulombs is the flow or the charge. So that's, we'll just have the sign here, 15 coulombs over 5 seconds, which is 3 coulombs per second, or 3 amps, isn't it? I'm not going to do the second part. It's much the same. Do exactly the same thing. Find the potential difference, if you like, or the difference in charge. which was negative 10. Negative 10 once again over 5 seconds will be 2 amps. Using the values given in 3.21, I'm not sure where exactly that is, but I think this is more or less, is this using the same formula? Yeah. Okay. Not going to go through that. Let's have a look at this one though. 10 to the power of 20 electrons flow past a point in 4 seconds. So rather than do that, we've got to work out what did we have? The number of electrons times the charge of an electron over what?
T.
Over T is equal to I. Because in other words, the charge is equal to the number of electrons times the charge of an electron. Okay, so let's fill in the blanks. We have the number of electrons. Write out what we know, please, is 10 to the power of 20. We have 10 to the power of 20 electrons. Flows past a point in 4 seconds. Calculate the amount of charge in coulombs that moves past a point in this time. Well, we don't need the time as such. We just need to use the number of electrons, which is 10 to the power of 20, times the charge of an electron, which is 1.6 by 10 to the negative 19 what? Isn't it coulombs? Yep. That's one electron has that much charge. So if I go ahead and do that, 10 to the power of 20, 10 to the power of 20 times 1.6 by 10 to the power of negative 19. 16, is that what you got? Yes. So we've got 16 coulombs of charge. The amount of charge that moves past a point in this time, 16 coulombs. The current in amps, well, we now can refer to this. We've got 16 coulombs of charge in 4 seconds is 4 amps, isn't it? Okay. Question 9. 3.2 coulombs flow past a point in 10 seconds. Calculate the number of electrons. Well, we want to refer to this formula, and I can rearrange that formula as the number of electrons is equal to the current times the time divided by the charge of an electron. We know what this is. This is a constant. But the charge is I times T. So I times T, or the charge, is 3.2. So the number of electrons is 3.2 coulombs of charge divided by 1.6 by 10 to the negative 19. Now let's try and do this without a calculator. First of all, 3.2 divided by 1.6 is what? 2. Now let's do that. That's 2 over 10 to the power of negative 19. Okay. 10 to the power of negative 19. Now if I was to do my index laws, what would I do with, well, that's like 2 times 10 to the power of 0, if you like. What could I do with this? Isn't that 2 by 10 to the power of 0 minus negative 19? Which is equal to 2 by 10 to the power of 19, what? Electrons, isn't it? So we've done that without the use of a calculator. There is a reason why we've done our index laws, of course. Or, of course, we could do, if you want to do it the long way, 3.2, oops, 3.2 divided by 1.6 by 10 to the power of 19. Oh, that's a negative 19, duh. Okay, I'm going to press enter there, and I'm going to fix that as negative. Oops. Negative 2 by 10 to the power of 19. It'd be nice for you to start using your brain a little, and maybe those calculations you probably try to avoid using a calculator. Which of the circuits shown in below would enable you to measure the current flowing through the bulbs when the switch is closed? Would you connect, what did we discuss? Would you connect what would happen if I connected an ammeter like this? Wouldn't the electricity just flow through the path of least resistance? Yeah. Okay, so is that going to measure the current? No. Absolutely not. So, no, it's not that. So I want you to start thinking about that. What about over here? If I close this switch, what's going to happen? Am I going to be measuring anything? No. Well, the ammeter though, if the switch is closed, this ammeter, which of the circuits, well, you have to read the question carefully, would enable you to measure the current passing through both light bulbs? So which one is it? B.
Why wouldn't it say? Because is the switch?
Well, because if the switch is closed, then that light bulb isn't part of the loop, is it? Okay. So electricity is going to flow this way, conventional current flow. Okay, it's going to go through there. It's not going to be through the light bulb. So of course it can't be C. If I can't connect, that's not going to measure anything. That's just going to create a short circuit. Electricity is going to flow through here, through the ammeter, and of course through there. It's not even going to go through any of the bulbs in that case. So of course the answer is B. Okay, now that's 17 minutes worth. I'm going to stop that video there unless there are any sort of questions. And I hope that you can at least realise that charge, or the rate of flow of charge, is current. We can then work out that in terms of number of electrons and things like that. You also need to be able to, if I were you, memorise the charge of an electron. You're going to use this over and over again, so I don't want you to be referring to that, is 1.6 by 10 to the power of negative 19. You're going to use that a fair bit. All right, I'm going to stop there.